Okay, welcome everybody. Thanks for making it out on for the first session of the morning. This talk is Java Language and Platform Futures. So I'm going to be talking about some of the things that we've been working on recently and where we're taking the Java platform. 5 years ago or so, people expressed concerns of whether the Java platform had a future at all, that whether Java had reached the end of its line. I think we've confounded those expectations. But the good news is, in addition to all the great work we've been doing recently, the long-term story for where Java is going is probably as good as it's ever been. So I'm going to talk about some of the things that we've got in the pipeline. The flip side of doing a sneak peek talk like this is, because it's a work in progress, everything I say might be wrong, but that's okay, right? So you've seen this slide a lot, right? Ordinarily, we speed past this and make some comment about the lawyers made me put this up, but today I want to focus on this slide. Right? This is speculative. This is for informational purposes only. This is not a commitment. Everything I say might be wrong. Okay? I want to make that very clear. In particular, the one thing I want everyone to not assume is that any of this will be scheduled for any particular version of Java. I don't want to wake up tomorrow morning and see Twitter posts about, oh, Brian Goetz says XYZ is coming in Java 10. None of this stuff is scheduled for any particular version, right? So there's a bit of audience responsibility that not to post incorrect or misinformation. This is just a snapshot of where we think we might be going. So with that, we all on board? Everyone agree? Sign the paper? Okay, good. Let's get started. All right. So as everyone has undoubtedly heard, Java turned 20 last year, and over those last 20 years, Java has been declared dead almost more times than I can count. And we've managed to continue to confound those expectations because we've managed to evolve, to stay relevant to the problems that people want to solve and the hardware people want to run their programs on. So don't know where Java is going to be in 20 years, but what I do know is we're going to continue to evolve the platform so that it stays relevant and vibrant. So fortunately, we have some principles that guide us along that evolution. So you've seen these slides before probably. 10 years ago, Graham Hamilton outlined some core design principles for the Java language, and we still look to these principles today as we think about how to evolve the platform. And you could summarize them as readability, simplicity, and transparency. And in some sense, they're all the same thing. It should be easy to look at code and know exactly what's going on, to not have to reason through what's going on here, what's going on there, because if you can't read code, you can't maintain it. And then, it becomes fragile, and eventually it has to be thrown away. Successful code lasts a long time, and over that time, it's read over and over and over again. So the code that's easy to read is also cheap to maintain and has a long lifetime. Code that's hard to read means we're likely to introduce bugs when we go to maintain it, and then people are going to say, let's throw this junk out and rewrite it. So this focus on reading code is an indicator that Java was aimed at building successful long-lived code, not just banging out disposable code. So evolution was also always in Java's DNA. Hamilton made it clear that we were planning for the long term, that we're going to evolve, but do so cautiously. So, rather than try to guess the future or follow fashion, our approach is a more conservative one, where we focus on the real-world problems that developers are facing today, and we look to solutions that have been proven, in other environments, rather than just jumping on the latest fashion. So the goal is not to add as many features as possible, but to add as few as needed to meet the actual needs of developers while staying true to those principles of readability, simplicity, and transparency. So we don't want, usually, to be the first language to add a given feature. We kind of like to wait until we have evidence that it's actually an improvement and have a good understanding of how it fits in with the other features in the language. And, if our goal is to enable writing successful long-lived code, sometimes it's better to let other languages do the experimenting and then adopt selected features after they've been proven, to carry their weight. Since language features live forever, we have to choose them carefully. And so, to give you an example, a few years ago at Java 1, James Gosling told a story about why they didn't have generics in Java 1.0, and it wasn't because parametric polymorphism wasn't understood at the time or wasn't seen as important. It was because they hadn't found the Java way to do it. And sometimes it's better to do nothing now and preserve the chance to do it right later rather than risk doing the wrong thing now. And so it did ultimately take 10 years to add generics, which was a long time, but I think the generics that we got were a lot better than what we would have gotten in 1995, which might have been C++ templates or might have been patterns from beta, and we would be living with those mistakes. So before I talk about what's going next, let's look a little bit in the past of some evolutions to the platform we've already done. Now, some were big. Rebooting data abstraction through generics in Java 5, rebooting behavioral abstraction with lambdas in Java 8, rebooting application configuration and encapsulation with modularity in Java 9. So these were big changes. But for each of them, the story was the same. We identified what we saw as a major pain point. So for generics, this was the inability to capture enough type information in the code, which led to less safe and less reliable code. And the cure was better abstraction, namely parametric polymorphism. And the result was more type-safe, maintainable code. Now, when we added generics, did everyone have to rewrite their code? No, of course not. We did it in a way that offered migration compatibility. So a library could be generified, and then clients or subclasses of that library could choose to generify now, later, or never. And this is an important aspect of our formula, that new features should be enablers, but not necessarily forced to use them. So it's also important to realize that the mechanism and the goal are different things. Language features are a mechanism, right? They're cool, they're interesting, but the goal is making it easier to build and maintain reliable programs. Language features aren't an end unto themselves. And while the big stuff gets most of the attention, there are dozens of small improvements in every release, and these smaller features have similar goals. They have, They address a pain point. We've observed a pain point, we identify a solution, and implement it. And that's true for the big things like Lambda, and it's true for small things like try with resources. Whether a feature is big or small, the goal is the same: make it easier to build and maintain reliable programs. So let's start with some smaller features that we've got in the pipeline. I showed a few of these in the keynote. I'll go into a little bit more depth today. And these are those that are aimed at improving everyday developer productivity. And it's, like I said, it's really easy to focus on the big stuff like lambdas, and it's obvious why. They're big and they're interesting, and as a language designer, they're big and they're interesting. So of course we focus on those things. It takes more of our attention, but the little stuff matters too. Now, again, usual disclaimer, this is a statement of direction, not a commitment to deliver anything, and certainly not in any specific release. When I say minor or smaller, I don't necessarily mean small. Some of these features are still pretty significant. They're just not in the reinvent the platform category that generics or lambdas were. And I'm going to show off three feature sets that we're working on: expanding the scope of type inference, reducing common boilerplate, and pattern matching. So let's look at each of these quickly. Okay, so let's start with type inference. Type inference is when the compiler can figure out the type of a variable from information in the program, from context, rather than making you type it with your fingers. Now, most of the time we like this because it eliminates redundancy while maintaining our commitment to strong static typing. Now, it's important to remember that type inference is not dynamic typing. When we infer a type, there's still a strong static type. We just didn't make you write it down in the program. So, is type inference good or bad? Well, sometimes it's good, sometimes it's bad. How do we decide whether it's good or bad? Does it make the program more readable and maintainable? Often, type inference removes noise from the code that's just obvious, and that makes the code more readable. Sometimes it removes essential information from the code, makes it less readable. So that means that as programmers, we have to use judgment. Sorry, no free lunch. So, we generally like to use type inference in implementation contexts. We're generally willing to accept more redundancy in APIs because APIs are contracts between, between bodies of code that might even be in different maintenance domains. So all of the techniques that we've used type inference for in the past and that we're going to in the future focus more heavily on the implementation of code rather than the APIs. So Okay, so let's look at where we use type inference today. In Java 5, we introduced type inference for generic method type arguments. So if you're calling a generic method like empty list, which is generic in the type of the element of the list, you could specify it explicitly like this. How many people here actually don't know this syntax? So now, for 12 years, we've had this feature in the language, and a lot of people have managed to avoid learning it because you almost never need to use it. That's really cool. That's really successful, right? So, you can write this like this, and this is how we all do it, and this is better, right? The extra explicit type witnesses don't add a lot of value. We know what it's a list of. We asked for a list of string. Why do we have to say string twice? Right? So this is a perfect example of where type inference offers a lot of value, and in the event that the inference produces the wrong type or is unable to produce a type, you always have the option of using the explicit witness, but most of the time you don't have to. So that's an example of type inference working the way it should. A similar thing we did in Java 7, we expanded it not just to generic method arguments, but generic constructor arguments. So originally, if you wanted to construct an array list of string, you said list of string, new array list of string. Why do I have to say string twice? What else might it be? So in Java 7, we added type inference for constructor invocations. We called this the diamond feature, but it's really just another form of type inference. And again, this code is just as readable, if not more readable, because it's eliminated something that's really just redundant. And in Java 8, when we added lambdas, you can explicitly name the types of lambda parameters, and sometimes that's the right thing to do. Most of the time, you can leave them out, and the compiler will figure it out for you. Now, you may have to use explicit type arguments for lambdas more often than you did with generic methods, because there are times when maybe there's a method overloading and the compiler can't figure out which one of the overloads that you meant. So people might fall back to the explicit form more often for lambdas than they did with generic methods. But the general concept is the same. If it's obvious, let the programmer omit it. If it's not obvious, give the programmer a chance to make it explicit. So, given that these past uses of type inferences have pretty much been winners, it seems reasonable to consider new context for type inference as long as it doesn't conflict with our bigger goals: simplicity, readability, transparency. So, like I said earlier, we like using type inference to smooth out implementation details, but not so much in APIs. And the reason is that APIs should not only be clear and unambiguous, but they also should be stable. You don't want small changes in your implementation to turn into a change in the signature of one of your methods, which then might turn into a binary incompatibility. So explicitness really helps to maintain stability for APIs. On the other hand, in the implementation, we're willing to we're willing to be more loose because it only affects the implementation. So another place we can use type inference to smooth out implementations is the types of local variables, and they're pretty much a pure implementation detail, right? The local variables occur only in the body of methods, and the method has a contract, and this is just how the method does its thing. So if we use type inference for the local variables, we can replace the explicit type declarations with something more implicit, where we're still saying, I'm declaring a variable, but I'm not going to tell you the type. The compiler is going to figure out the type by looking at the type of the thing on the right-hand side. Now, at first glance, sometimes people freak out here because of the loss of type information. But tell me, which is more important, the type of a local variable or its name? If you want to be able to read a program and tell what's going on, which of those gives you more information? My claim is that it's the name. In the top version, the names are sort of scattered all over in the middle of the code. Whereas in the bottom version, the names line up nice and cleanly near the left margin. So we're putting the most important thing first. Now, this feature isn't new with Java, of course. People have been asking us for this for years because they like it in C# or Scala. So this isn't new. People who have used this in other languages swear they'll never go back. So we think this fits into our profile for where expanding the scope of type inference makes sense. It's been successful in other contexts in Java. This particular context has been successful in other languages. So we sort of feel like this is a feature that's ready to be promoted. Okay, so let's talk about boilerplate. Java has a bad reputation for being boilerplate intensive, and it's a deserved reputation. Now, taming boilerplate is actually a never-ending journey because every bit of boilerplate that you remove just makes the other boilerplate more obvious, right? It's kind of like, you get a new pair of, you replace your shoelaces, and all of a sudden you realize how shabby your shoes look, right? So you get new shoes, and well, you see where this goes. So, we've done some features for eliminating boilerplate in the past. Try with resources was one. Lambdas and streams eliminate a lot of boilerplate, but there's still a lot left. And so we're going to look at what the biggest sources are and attack them from the top. So, I think one of the biggest sources of boilerplate are what I call the state-driven methods for domain objects. The methods like equals hashcode, toString, constructor, the ones that have to do with initializing and inspecting the object state. And these can usually be generated formulaically. In fact, IDEs will do this for us, right? You say, generate constructor, generate getters, generate equals and hashcode, and the IDE just does it. And that's great, because that's, error-prone work that you don't have to do yourself, but that only helps with writing code. That doesn't help with reading code. And it's also easy to just cut corners and leave these methods out. How many people here have been bitten by methods with bad equals or bad toString? Right? Now, you know that the person writing that class knew that they were supposed to provide an equals and a toString, and they got lazy. And they got lazy not because, it was so hard to do, because they could have asked the IDE. I think the fact that this visually clutters our code deters us from doing the right thing. So if we can eliminate this clutter, maybe more people will do the right thing. So, a lot of classes are just, pure data objects. They're just dumb holders for data. They don't have any non-trivial behavior. They don't have any invariants or preconditions. They just hold the data. So, classic example, this is the only class I ever write, point xy. And, you'd like to, this is what being an architect is. This is all the coding you get to do. You'd like for this to be the end of it, because it's all of the useful semantic content of this class, right? It's called point, it has int, it has index, it has int y. What else do I need to tell you? Well, I need to tell you a lot, which is unfortunate because there's not a lot of information in all that extra boilerplate code that the IDE generated for me. So it would be nice to be able to say, this class is just a dumb data holder. This is the whole thing, int x, int y, and just give me a constructor, and give me equals and give me hash code and all of that. And of course, maybe I don't want the default equal, so that's fine. I just include it in the body of the code, and the compiler says, oh, you already have an equals method, I won't give you one. So this seems like a nice idea. Of course, the devil's in the details, right? All of the hard parts of doing this are, how do we deal with, allowing the user to tweak the definition of equals, right? Let's say you have one of your fields as an array. Should you compare equality by, are they the same array by identity, or are they the same array contents? Well, for either of those choices, I can find cases where one or the other is the right thing and the other is the wrong thing. So people are going to need to be able to do both. We need to provide mechanism to allow people to fine-tune these things. That's where all the hard work in this feature is, right? It's easy to say, wouldn't it be great if I didn't have to write these things? And then the easy cases are easy, and then the hard cases are where all the complexity is. But it's not just about boilerplate. One of the things that makes this an attractive feature is it's not just eliminating code, it's raising the level of abstraction. It's saying declaratively, I am a domain object, and therefore domain objects behave in this way, I behave in this way. And this allows the compiler to sort of infer more about what's going on, and this connects with other features, and stay tuned, we'll get there. Like I said, there's a lot of details to work out. How do I add validation to the constructor without rewriting the whole constructor? How do I tweak a quality comparison without rewriting the whole thing? There's 100 what ifs. What if I want the fields to be private? Where do I put annotations? Where do I put JavaDoc, etc.? But when you kind of pull on that string a little bit, what you see is there's a deeper problem here, which is there actually a compact way to declare the state-driven methods? And if there is, then these data classes are really just macros for classes that use a state-driven mechanism for generating these methods. So stay tuned for more detail as the project evolves. Okay, so let me talk about the last of the smaller features that I'm going to talk about today, and that is improvements to switch, or another way to look at this is pattern matching, if you are familiar with pattern matching from other languages. How many people here have seen pattern matching in Scala or in functional languages? All right, so a lot of you have seen this. A lot of you like it, right? A lot of people say, when are we going to get case classes? So let's look at the switch statement that we've got right now. It's you can think of it as a generalization of the conditional operator, but it's very, very limited. It's limited that it can only have statements in the body in a case arm rather than expressions. It's limited in the set of types you can switch over. You can only switch over ints and strings and enums and a few other well-chosen types. It's limited in the set of conditions you can test with case. You can only test for comparison for exact equality against a constant. And once you hit the limit of what switch can do, what do we reach for? We reach for visitor, right? How many people here use visitor? How many people here like visitor? Right, okay, don't have to say any more than that. People ask us for features all the time. We have a database of like thousands of RFEs. One of the most common RFEs we get is, can I have type switch, please? In actuality, people don't want type switch. They think they do because it's better than what we've got now, but what they really want is pattern matching. Pattern matching subsumes the constant matching that we've got today, it subsumes type matching, and it subsumes a lot more, including a lot of the use cases for visitor. So let's take a look at how we might evolve switch to incorporate some of these features. So as an example, can people read this in the back of the room? I don't know why I asked, because I can't make it any bigger if you can't, but I guess it's polite to ask. So here's a switch statement that is actually almost came from real code. I cleaned it up a little bit, but this came from some actual code that I wrote, where I was I was extending the ASM class file library to add some experimental bytecode features, and one of the things you end up having to do in ASM, if you've ever used it, is whenever it talks about a class file constant, it hands you back an object, and then you have to do this big if it's an integer, if it's a string, if it's a long, etc., for the enumerated list of class file constants. So if you write code like this, first of all, it's kind of big. But it's also error-prone, and I'll get into that. It's basically a more general mechanism than we really need. What we want is piecewise assignment. We want to be able to test a bunch of things and then assign a variable exactly once in each arm, but that's not what we're doing. We're using a general if, else if, which ends up being bigger and riskier than we like. So the first thing I don't like about it is it's less readable. Right? You have to read through the whole thing to realize that each of these if blocks is doing basically the same thing. It's also slower. It's guaranteed to be O of n, whereas a switch in the best case is O of 1. An annoyance that everybody complains about is after you do an instance of, the first thing you have to do is cast it to that same thing. I just did an instance of. What do you mean I have to cast it? Right? Not only is that annoying, but it's an opportunity to make an error, right? Whereas if there were a fused operator that did both, you wouldn't have that opportunity to make the error. In each of these arms, I'm assigning to a local variable. What if I forget? Will the compiler catch me? Well, maybe the definite assignment analysis will, but not the way I wrote it, where I assign a default value at the top. So I could easily make a mistake in one of these, and if it's a rare case, I won't even notice. And finally, that's just an awful lot of code to do something simple, right? So we've all written code like this. We've all kind of wished it was simpler, right? So this is an example of the kind of boilerplate that people complain about with Java. Okay. So how could we improve this? Well, the case label today means, is the switch target exactly equal to this constant? So what if we extended that to include a type test, right? So here's an example syntax, case integer x. What does that mean? Is the thing an integer? If so, cast it to integer, and then assign the result of that cast to x, so x is in scope in the body of the switch. So what would the example I just showed you look like under those rules? Well, it's better, right? The code is already getting smaller. The type test, and this is actually a pattern. What that means is it combines a predicate of testing the target to see if it matches, and if it does match, it's able to bind pieces, to destructure the target and bind pieces of it to some local variables which can then be used, right? So this is an improvement. I've fused the instance of and the cast. And it's also more clear that I'm doing the same kind of test in each arm, right? The conditions in all of those else if, all happen to have the same structure in the first example, but here, because I'm using a more targeted language mechanism, they're forced to have the same structure, and that's less error prone. So when I say case integer I, that variable I is then in scope in the for that case arm, so I can just freely use it, in the string.format format. So, this is getting better, right? We've limited some boilerplate. Potentially switch could be O of 1 instead of O of n, time complexity. We can actually do better here. So what we really want is some kind of piecewise definite assignment. So can we bend the switch statement to do that? And I think we can by allowing switch to switch not only over statements, but over expressions. So I've picked a syntax here. Don't get caught up in the syntax. But I use the arrow instead of the colon to indicate that the result of a case arm is an expression. And then the whole switch statement evaluates to that expression. So I switch on the constant. If it's an integer, then the switch evaluates to this string.format. If it's a byte, then the switch evaluates to that string.format, etc. So the code has gotten a lot more compact, it's gotten a lot more direct, and it's gotten a lot less error prone. And it's the error prone part that I care about. I know you care about the boilerplate part. I really care about, can we make it easy to write clear error-free code? But it is an awful lot less code, and I think it's a lot more readable because it's not obfuscated by all the details of the instance of test and the casting and having to assign something to a local variable in the middle of the arm, and etc. All right, so those examples showed off a lot. We showed off expression switch versus statement switch, switching on an arbitrary type, not just the 9 or so blessed types that switch works on, and using type test patterns as case labels instead of just constant case labels. But actually, there's sort of a rich vein of stuff that we can mine here to make this even better. Now, probably these won't all come at once; they'll come out over time. But this is a feature that really has legs. Okay. So let's talk about how how this might get fancier. So we talked before about data classes, how data classes commit that I am a domain object. They make somewhat of a commitment to their state being their representation being coupled to their constructor signature, which means that you can reverse the operation of construction. Right? Construction takes the fields, creates an object. The opposite of that is take an object and bring it back to the fields. For an arbitrary Java class, you can't do that, but for domain objects, you can. So we can exploit that by wrapping, by using, to give us what we call these constructor patterns, where we can say, is this thing equivalent to what I would have gotten if I called the point constructor with x and y? And if so, cast it to a point, extract its x and y fields, and bind them to local variables. And this is something that the compiler can automatically do with data classes. If you've seen case classes in Scala, you're asking what took you so long. Let's do an example of this. Now, this is a slightly more complicated example. The example is sort of a typical, I'm representing the expression as a tree. So I have an abstract type called node, and there are subtypes of that node: constant node, plus node, negation node, multiplication node, etc. And I want to write, a method to evaluate an expression. So I can express that very clearly with switch and with patterns, with these constructor patterns, where I can ask, are you a plus node? Are you a multiplication node? If you are, get the left and right pieces and bind them to some local variables. So walking through the code, I've been handed a node I want to evaluate, and I switch off it, and I say, is it a constant node? If so, bind its constant to I, and just evaluate to I, because that's what a constant is. Is it a plus node? Okay, extract the left and right subnodes, bind those to some local variables, recursively call eval on each of those, add them together, and that's the evaluation of this plus node, right? How much code would this be to do it with visitors? Too much, right? Is the visitor code more clear or less clear than this? Well, once you learn to read this stuff, it's a little bit new, so it looks a little scary. But once you learn to read it, it's much more clear because everything's right here. You don't have this multiple layers of indirection that visitors give us. And so the key here is this constructor pattern, which fuses the instance of check, the cast, extraction of the relevant fields, and binding them to local variables. But because this matches the shape of the constructor for a domain object, it makes intuitive sense. Are you a constant node with this parameter constant? We can actually take this farther. I don't want to dive too deeply into this, but you can actually take this farther because patterns actually nest pretty nicely. And so you can ask more complicated questions like, are you a plus node whose left subtree matches the pattern constant node with 0? Using this mechanism, most uses of visitor pattern can be eliminated and reduced in complexity and size. Like I said, probably these features will be, will not all come at once. We'll start with type test labels and probably get fancier from there. Okay, so now let's look at some bigger stuff. So everything I'm going to talk about now, actually, I've talked about before, actually here. If you saw the version of this talk from 2 years ago, you're probably going to be wondering, gee, haven't they made any progress since then? This looks awfully similar to what he was talking about 2 years ago. This is the nature of big evolutionary projects. So to put this in perspective, I have literally spent thousands of hours thinking about Proiect Valhalla, which is what I'm going to talk about next, value types and generic specialization. And what I'd say is I've just about got the problem loaded into my head. This is not small stuff. The diagrams I'm going to show you now are going to look a lot like what I showed you 2 years ago. What we've been doing for the last 2 years is understanding what are the consequences of putting this into the language in the VM. Okay, so what's Proiect Valhalla? Proiect Valhalla is about rebooting the layout of data in memory. Okay, why is that important? That doesn't sound particularly interesting. The reason it's important is because hardware changes. In the last 20 to 30 years, hardware has changed dramatically. So just give you an example, 30 years ago, if you looked up what's the cost of an arithmetic operation in your processor data book, and you looked up what's the cost of a memory fetch, you'd find out that they were about the same thing, roughly 4 cycles each at that time. Since then, the relative cost of these two operations has expanded by several orders of magnitude. A cache miss now costs you on the order of 300 clock cycles. Typical processors, like the one in this laptop here, can issue 4 instruction arithmetic operations per cycle, which means that a cache miss potentially costs you 1,000 instruction issue slots. So 2 things that cost the same 30 years ago, one costs maybe 1,000 times as much as the other now. So there's a good chance that the decisions we made about laying out data in memory 25 years ago are probably not optimal for today's hardware. And the big cost is indirections, pointer fetches. And the reason we have to do so many of those is object identity. So with the exception of the primitive types, in Java, everything is an object. Objects have identity. Identity serves things like polymorphism and mutability and locking, which are useful things to do, but not all classes need that. In particular, the point XY class that I showed before doesn't need that. It's just a point. It's not, it doesn't need to be mutable. It doesn't need to be polymorphic. It doesn't need to lock. It just wants to carry some data from one layer of an API to another. But if we have a model that says everything's an object and all objects have identity, everybody ends up paying for identity whether they use it or not. So how do we pay for it? We pay for it by having a layout in memory that's not necessarily something we want. So again, the only class I know how to write, final class point, final int x, final int y. How is this going to get laid out in memory? Well, I have an array of points, and so that's arrays are objects. They have object headers, and the elements of an array are references to a point. So each of those points is an object with an object header. And there's no mutability or polymorphism here, but we ended up with this layout because, well, maybe there will be, right? And the costs, so if you look at like the memory density that we get out of this, it's kind of lousy, right? We have 2 words of payload, x and y, and we have 2 words of header as overhead and a word of pointer as overhead. So that's like 150% overhead for representing an array of points like this. At the same time, these points are all allocated in the heap. That means more allocation, more garbage collection. And then the real cost is the loss of locality. If I want to walk through this array of points, I'm going to be doing a dependent load to get to each of these points. And that means I'm risking taking a cache miss every time I go. So this, harmless seeming idea, everything's an object, objects have identity, leads us to a memory layout like this, which as hardware evolves 20, 25 years later, turns out to be highly suboptimal. Now, sometimes you don't care, your data sets are small, your program isn't compute bound, but if you're doing data-intensive work, analytics, big data, this hurts a lot. It both hurts in terms of how much data you can load into memory, and it hurts in terms of what it costs to crunch on that data. Now, when people hear about this, sometimes developers do things like this. Let me shred those XY points into 2 arrays so I get better locality, right? And sometimes you actually need to do this because you have real performance requirements. Sometimes it's just some bizarre obsessive compulsive disorder that programmers seem to be prone to. But it happens a lot that developers will crap up their code for performance reasons, even though they don't have any reasonable performance requirements or metrics in place. But they know that the other way is slow, so they end up writing bad code. And, doing this means your code's less readable, it's more error prone, it's less maintainable, and we sort of feel like this stems from this bad choice that people have been given, which is you can either have abstraction or performance, pick one. And in general, developers pick wrong every time. So if we don't put them in the position where they have to make this choice, maybe they won't shoot themselves in the foot. The problem is we can't figure out that no one will ever lock on an object, so we have to lay things out pessimistically unless we get some help from the programmer who says, look, I really don't need polymorphism, I don't need mutability, I don't need locking, I just want some data, please. So the layout that we want is most of the time is this. Just give me the data, lay it out in memory, I want an array of structs, please. So what kind of code do we want to write in order to get this layout? And what I claim people want to do, or should want to do, is to say something about the class. This class is just data. It's a value. It should be treated like a value. It should be compared by its state, not by its pointer identity. And that is what enables the VM to lay things out like this, where values can be inlined into arrays that can be inlined into other values or objects. So, this is the motivation for Proiect Valhalla, which is that, as Master Yoda tells us, identity leads to pointers, pointers leads to indirection, and indirection, of course, leads to suffering. So, value types. Core feature of Valhalla, value types. These are just pure data aggregates, just the data, no identity. We compare their equality by 2 points are equal if they have the same x and the same y. We don't allow representational polymorphism. You can't extend them. They're not mutable. They're not nullable. Now, these are restrictions that not every class will be able to take, but a lot of them can, right? We write classes that fit into this category every day. And by giving up on identity and the other things that identity enables, like mutability, it allows us to get the layout we want. Values can be routinely flattened in memory. We can squeeze out all those object headers. They all go away. And we end up with things that, behave like classes in that they can use encapsulation and methods and constructors and all of those abstraction tools that classes are good for with the runtime behavior of primitives. So they're better than primitives because they can have methods, they can have fields, they can have constructors, they can implement interfaces, they can use encapsulation, their fields can be private, they can use generics. So all of these great tools for abstracting over data that we get from classes, you can use with values. And they have this nice memory behavior like primitives. So for a lot of classes, like our point class or like most of our domain objects, it's kind of the best of both worlds, right? Now, there's a lot of devil in the details here, but a quick way to answer kind of any question about value types is imagine how would it work with int? What would int do, right? What happens when you assign an int to object? It boxes, right? What happens when you assign a value to an object? Boxes. So there's kind of like two ways to look at this. You could look at this as faster objects that have some restrictions, or you could look at it as better primitives, right? So you could, you know, either view of this works. But our sort of mantra for this is codes like a class works like an int, right? Best of both worlds. Don't put people in a situation where they have to choose between abstraction and performance. Okay, so who would use these? Well, everybody. Application writers that deal with large data sets would use value classes so that they could reduce the memory footprint of their data set and reduce the number of indirections, get a flatter data set that they can work on with better locality. Library writers will use this all the time, both in their implementations, like we can make hash map faster by just having the internals use values for the map entries rather than objects for the map entries. So we rewrite hash map, every Java program gets faster, no API change. That's great. There are also a lot of useful abstractions you can expose as values. So things like alternate numerics, big decimal, or unsigned int, STL-style cursors, algebraic data types like optional. It's possible to implement these with value types so that they're expressive and powerful and type safe and all of that, but much faster. If you're a compiler writer, you're going to love this. People who build compilers for JavaScript and Ruby are on the JVM are constantly fighting with the fact that the numerics in Ruby are not the numerics that they have in Java, so they can't translate Ruby ints to Java ints. They have to translate them to objects, and they're much slower. So compiler writers can write language runtimes using value types that don't pay that object penalty and end up with faster code. It's an obvious substrate for implementing features like tuples or multiple value return or wrapping native resources. So compiler writers will like this too. So my argument is this is good for everybody. Even though it seems like a low-level feature, it's actually something that will find benefit at all the layers. So, okay, so how could this be so complicated? How could you be working on this for 2 years and we haven't seen any results? Well, this is the string. It seems simple enough. It has all value types come from all the same motivations why we have primitives, but it's deeply intrusive into everything. At the VM level, we have new bytecodes, new type signatures. At the language level, it interacts with everything. So if I'm going to have value types, well, I'm going to want to have generics that's over value types. I'd like to have an array list of int and have it be backed by an int array, not turn that into an array of boxed integers, because otherwise I'm back to the same memory layout that I showed a picture of before. So we have to figure out how generics interact with values, how do wildcard interact with specialized generics. What's our top type? Is everything an object? Well, maybe not. So we don't want to just nail these things on the side. We want to integrate them in so that they fit in sensibly and compatibly. And that's where all the work is, right? All the things that it's connected to that makes it look not nailed onto the side. So like I said, with generics are expressive enough, right? If you want to express list of int, you can just say new array list of integer. No problem. It works. It does exactly what you mean. But it's slow, right? every integer in that list is like, you know, the picture with the points, the array of points I had earlier, and you end up with all of the same overheads. The memory usage of the object headers, the indirection to get to the data, the loss of locality, extra allocation, extra GC. So for all the same reasons that we wanted value types, we want specialized generics over value types. And, you know, if we couldn't make these play nicely together, it would be pretty lame. Also, who uses stream? Okay. Who finds the hand specializations like in-stream and long-stream annoying and kind of like ugly? Yeah, that's what I thought when I was writing them too. I don't want to do that ever again. Oh, I let it slip that I write code bigger than points. Sorry. That was horrible, right? It was necessary because you know, there would have been no easy way to add up a list of integers without it, other than reducing over boxed, you know, boxed ints. But it was something we had to do, but not something we wanted to do. It was more code, more footprint, more bugs, serious design constraints on stream, and there are features we didn't get because of that, and less abstraction. The commonality between stream of integer and int stream is a lot less than you'd like it to be, right? So that was a big, big compromise that we had to do in that library and in other libraries that people write every day. You know, anybody used the Goldman Sachs collections, now Eclipse collections library? You know, they had to, you know, they took a template-based approach where they generate mechanically specialized versions of all the collections over all the primitives, you know, 81 map implementations. It's horrible, right? But people, they need the effect of that. They just don't want the code footprint of it. Okay, so how does this look? Well, if you're specializing over a broader set of types that include references and values, actually the set of operations you can do is restricted because there are some things that aren't supported by both refs and values, like synchronization, right? If you have generics today, you can synchronize on a T because T is always object. But what if T could be int? Then you wouldn't be allowed to do that, right? So the compiler has to know, are these the old generics where it's just references, or are these the new generics, which is references and primitives and values and maybe even void? So you have to label the type variables such to say this is generifying over a broader set. That's what this any modifier does. And then thereafter, it looks mostly like regular generic code. So I talked about the string. You know, you know, when we added generics, it was important that the existing classes could be compatibly generified without forcing a flag day where everybody had to recompile their code and generify their code all at once. We've got the same constraint here. When we convert collections from old generics to new generics, whatever that's actually called, that anyfication needs to be binary and source compatible. We need to be able to anyfy our libraries without forcing everybody who uses list or has subclassed list to immediately anyfy their implementation. And like I said, this is where most of the work is ensuring this kind of compatibility. And there's an awful lot of work fixing up our libraries so that we can merge in-stream into being just stream event. Okay. So what's Valhalla about? Well, you could say it's about performance. Make object graphs denser and flatter. So we have fewer object headers, less indirection, less allocation, and GC. And so how do we do that? With value types, we extend generics to work over values, and we anyfy our libraries. Okay, great, good story. You could also say Valhalla is about better abstraction, about caulking the seam between references and primitives so that you can make generics more powerful, generify over everything. Generify over references, primitives, values, and even void. So, like, how many people here have noticed that there's 9 versions of arrays.sort in the JDK? Now, that's not fun for the person who had to write it, not fun for the person who had to test it, and annoying for the people who have to use it, right? So, win all around, right? We'd like to be able to write it once, test it once, have it work once. And again, you know, the goal is stop making people choose between performance and abstraction, because if they don't have to choose, then you won't be tempted to hand unroll your array of objects into twin arrays. You won't be tempted to write specializations like in-stream, and generics will just, you know, be the primary tool of choice for abstraction. So that's where we want to get to. Big project. Okay, let me talk briefly about the other big project we're working on. We did a demo of this at the keynote, Project Panama. Project Panama is about rebooting the interface between Java code and native code and data. So calling native code, accessing data out of the native heap. So today, we do that with JNI, which is unpleasant, error-prone, slow, and insecure. So let's do the opposite of that. Let's make it easy, secure, and fast. Who thinks that's a good idea? Yeah, right. So we want to make it easy, safe, and fast to access code out of the native heap, going through Java interfaces, to call out to native code, to get rid of all that JNI and replace it with stuff that's been generated by tools, which can then be more easily optimized because the VM can see all the way through it. And this makes it possible to use a native library as easily as using a Java library. So what do we have to do? Well, right now with JNI, we have this long workflow where you look at the target API, you figure out how you're going to model it in Java, you implement some wrappers, then you have to implement some C headers, and then you have to implement some C implementations, and you get out of that, you get a shared library that you can then eventually call. So let's get rid of all the steps that involve manual stuff and replace it with tools where you point a tool at your header file, it extracts the calling sequences and the struct layouts, and it generates a jar that has interfaces in it. And you just program against that as if it were a Java library. Sounds good, right? So I did a demo at the keynote. I'm not going to do the full demo here, but basically what we did here was we took the OpenCV library, which is a C++ library for image processing. We wrote a simple program in C to call it to look at an image and detect if there was a picture of a cat in it. And then we wrote the same program using JNI and then with the Panama tools. So the C code was about, page of code, pretty straightforward. Read the image in, pass it to the library hands you back a list of rectangles, you draw the rectangles on the image, and then you draw the new image. The same thing in Java is almost the same, maybe 20% bigger, but pretty much exactly the same code. And the library returns things like pointers to structs. That comes back as a generic abstraction of pointer to some interface type that represents the struct. It may look like it's slower because you're doing these indirections through interfaces, but in fact, at runtime, the VM generates binder code to access the native. It all gets compiled down to direct memory access. It's way faster than JNI, and it's safer. To give you an idea, here's half of the Java code, the JNI stubs, and that's not good. Well, the code's horrible. Right, lots and lots. Wouldn't even fit on this screen if it were actually on this screen. Demo fail. Didn't even do a demo and it failed. All right, so and when we run it, it just works, right? It finds the cats, draws the picture. Yay, everybody loves cats. So Project Panama is actually fairly far along. The demo that I showed at the keynote is actually real. It actually works. And there's a OpenJDK mailing list, Panama Dev, if anybody's interested in getting involved. But it's really, really cool stuff. And with that, we have about 7 minutes left for questions. You can send your questions to Twitter at this hashtag. And I think there's a microphone, and people are already queuing up at the microphone, aren't they? Or are they just trying to leave? Well, if anybody's near the microphone and wants to ask a question, go ahead. No, they really just want to leave. You can leave. Just do so quietly so other people who want to ask questions can ask questions. Where is the microphone? It is up in that corner, right? If you're standing near the microphone and you're in the way of people who want to ask questions, it would be nice to step out of the way. Oh, we have a handheld microphone. All right. Fall back to old technology. Who has a question? Raise your hand.
Do you envision something like partial parameterization for lambdas, which you see in functional languages?
Do you mean partial type inference, where it infers the types for some of the variables but not all of them? Or do you mean partially evaluating the...
Yeah, the latter one. Yeah.
Not a high priority. There are other things that are way higher priorities. There's nothing intrinsically wrong with it as a feature, but from a return on complexity, we think there are other features that are more valuable to focus on. That, by the way, that's the answer to like every why didn't you do X question. Well, actually, no. Some of them are like, it's because X is dumb. But plenty of them, the answer is not X is dumb, but there's infinitely many things to do. There's finitely many of us, so we have to prioritize. And the answer is almost always there were other things that we thought were more important. Okay, more questions.
For the Scala people, which I call myself a little bit, where do you draw the line with regards to stopping certain features? Like with the pattern matching, you can go quite far and put a lot of stuff in.
Yeah, so you know, a lot of the features that you saw today, you might have thought, oh, they're just stealing features from Scala, aren't they? And there's some degree of that. We kind of view other languages that have a little bit more of an experimental bent to them as great laboratories for figuring out what works and what doesn't. There's lots of things in Scala that work. There's lots of things that don't seem worth the complexity. And so we kind of cherry pick the things that are easy enough to transplant into Java. So pattern matching is something that transplants very cleanly without dragging 47 other features with it. And it's also something that I think object-oriented programmers are pretty much ready to accept, right? You know, it doesn't require a big paradigm shift about how you think about your program. It's something that fits fairly nicely into object-oriented programs. So that was an easy one to scoop up. It's also one of the most commonly requested things that people say they wish they had from Scala in Java. So it wins both on the not connected to 47 other things and the it's something that people really want. And as the example showed, you know, it really does squash down some real world code into pretty readable stuff.
And do you see like simple pattern matching as something you can evolve later to more complicated versions?
Absolutely, right. If we just did, I mean, people have been asking for type switch for years. So if we just did that, we'd make a lot of people happy. Right? If we went one step further and just did constructed patterns and no nested patterns, that would make more people happy. You know, so there's many opportunities to go deeper. It's a pretty rich vein.
Okay, so in Java, all of this will make Java more fun, of course. Great job. So, but one thing I see from Scala, a lot of frameworks right now in Java depend heavily on reflection. And in Scala world, a big shift is happening. Libraries more and more get rid of reflection. They use, full macros, but it seems to be, I would say, less error-prone. Are you thinking about moving in this direction in the future in Java?
You know, in theory, that sounds wonderful. It took Scala a long time to get there to where mere rocket scientists could write correct macros. And, you know, the Clojure community has, you know, similarly, you know, it's taken a while to figure out how the macro facility should work. It seems like it's a big stretch for Java.
Could I add one little comment?
Yes, please.
One thing we're definitely looking at is ways to support frameworks with alternative reflection techniques. Core reflection has kind of had its run. I think there could be a lot of mileage in method handles and variable handles going forward where reflection is based more on a capability mechanism rather than the rights-based mechanism that we've got in core reflection. But there's a whole other talk in that.
Well, and similarly, you know, one of the challenges about reflection is that it's really reflection over class files. And that was, you really didn't notice that when, in the early days of Java, when their class files and source classes were so close to each other. But, you know, then when you add things like generics and bridge methods and generic methods, it's much harder to use core reflection to figure out what source code did this come from. And what that suggests is we need a higher level reflection mechanism that actually reflects over the language level type system, not the class files.
Hi. With the type inference, it seems like you want to prevent the developer from writing in-readable code. But should that not be the responsibility of the developer and moreover also of the team of the developers to keep the code more readable? And therefore you could maybe introduce type inference at more places.
So I recognize it's impossible to prevent people from writing unreadable code. So, that's kind of a fantasy to think we could do that. But more seriously, this is a trade-off, right? This is a trade-off between programmer convenience for writing code and the stability of the Java ecosystem. And so, things like using var in the return position of a method is probably what you're thinking about. No, we're never going to do that, right? Because that makes libraries unstable. That leads to dynamic failures that are hard to predict because people will make tiny changes in the body of the method which ripple into a change in the method signature, which means classes compiled against older versions of that library that dynamically link to the new library will fail to link at runtime. And that makes Java less reliable, and we don't want to do that, right? So it's not so much about protecting people from writing unreadable code, it's about protecting the ecosystem from unstable code. I think time's up, so thank you very much.